Can the hard detection systems be used to detect avalanches? This is a presentation by me, Dylan Baker. So in this presentation, I will focus on the ground vibrations that are created by avalanches. Start off with an introduction, and I'll explain some of my previous research on Lahar detection systems. I'll then explain my experiment, the data that I got, and my conclusion. So, on roadways that go through mountain passes, avalanches that go onto the roadway are becoming a serious problem. When civilians driving a car on a highway go around a turn, they could drive right into an avalanche that has gone onto the roadway. Right now, there's no way of knowing when an avalanche happens in one of these passes onto the roadways, except for cameras. At the top of some passes, there are several cameras that point at the roadway. However, these cameras have to be monitored by people at all times in order to detect avalanches. The only other way road crews know about avalanches is by word of mouth. So there's a thing called acoustic monitoring systems, and acoustic monitoring systems use an accelerometer buried underground to detect lahars. Lahars are fast-moving mud flows created by an exploding volcano when ice melts from the side of the volcano. So an acoustic monitoring system works by having an accelerometer buried deep underground, and when the accelerometer picks up ground vibrations from a lahar, it sends that signal using an antenna to a computer in an offsite facility. In that facility, the computer measures the vibrations that the sensor picked up and determines if it is a lahar or not. It then sends out an alert if it is a lahar. So my experiment was to measure the ground vibrations from avalanches, because since lahars have unique ground vibrations, and if avalanches have unique ground vibrations, then you could use lahar detection systems to detect avalanches. And so I had to first figure out if avalanches have create unique ground vibrations. So what I did for my experiment was I buried an accelerometer 6 inches underground, and then I caused an avalanche 5 feet away from the accelerometer. I then repeated these steps at 10 feet and 20 feet away from the accelerometer. Although in order to prove that they were unique, I had a car drive by the accelerometer to make sure that a car passing on a highway wouldn't be detected as an avalanche. So on the bottom half of the graph, you can see the results I got for the avalanches. The accelerometer moves quite a bit. It jumps up and then it waves as it waves and dips and drops as it finally peters out. And most of my data for the avalanche follows that general thing, with a peak and then a couple of bumps as it goes down. The cars, however, would go up and then down gradually, with not a lot of peaks or dips. That's because when a car drives by, the vibrations become larger as the car gets closer to the accelerometer, and then becomes smaller as the car moves away from the accelerometer. For an avalanche, different chunks and amounts of snow are falling and sliding at different times, creating the variation in the data we have. So what I proved by this is that not only do avalanches have different vibration waveforms from cars, but that they also occur at a different frequency. As can be seen in my graph, they were at different frequencies compared to the cars. So I've also proven that avalanches can be easily picked up by an accelerometer. In the future, these acoustic monitoring systems could be implemented into passes to detect not only avalanches, but potentially rock and landslides. Thank you.